symbiotic relationship. The data science also requires biology and medicine because we provide so much inspirations with new sequencing data coming through with new data type, with the complexity of biology itself, with the many things that beyond the biology, the policy side and human side of informatics that all make the BIOKDD very interesting. So I hope that you bring the excitement, continue throughout the day, and think about how we can build this community better. We can build it better by perhaps getting the BIOKDD to fit with a new format. Virtual perhaps is going to be a theme to stay. And I'm hoping that we have some discussions at noon during the lunch break. Feel free to bring your lunch and we'll just have a chat about it. And also perhaps we need to build a stronger community. So I also want you to think about how we can just not only come here, but also just during the non-workshop days, think about this community becoming a bridge between ACM, AMIA, IC, ISCB, and so many other organizations in the intersection. Okay, well, I think I'm done with my just introduction. Should we begin our regular session?
Yes, I think so. It's your turn to present, so you can start sharing your slides.
Okay. All right, today I'm going to present our work related to COVID-19. We actually developed a database resource for the community. It's called PAGER-COV. And PAGER-COV is a comprehensive database that contains pathways, annotated gene lists, and gene signatures for anyone interested in coronavirus-related disease biology studies. So this is a work collaborated within the UAB Informatic Institute, and also one of the collaborators is from University of Wisconsin-Madison, Clark Hsu. So I want to actually give you some background on the biology side of SARS-CoV-2, because this is a data science conference that I felt people normally just treat the data very passively. But the biology is started with something very simple. So the SARS genome only contains it's a linear RNA strand with 16 non-structural proteins that's encoded by two open reading frame, ORF1A and 1B. And then beyond that, you got this structural protein that form the protein shield. Right? So the most famous one that everyone knows is the spike protein. They spike out. The spike protein is responsible for attaching to the host cell, especially the ACE2 receptor in human, and hijacking that receptor for entry of the virus genome and then start infections and downstream event. And there are some other protein particles. People have been studying the whole class of a coronavirus for many decades. And SARS-CoV-2 is only one of the many the beta coronavirus in the family. So I think my point here is that if you want to actually understand how to design drugs and the diagnostic, dipping into the knowledge of biological studies in the past is very, very critical. For example, in the genome ORF1b, it encodes several proteins, and one of them is an enzyme called RNA-dependent RNA polymerase, or RdRp. It turned out that this protein is well conserved throughout the family of coronavirus, and that's the protein structure, and it's been solved even before the SARS-CoV-2 came into existence. So UAB and other companies and Gilead, as you all know, have been working on an inhibitor of this protein. And one of the famous one that's been used is called Remdesivir. In fact, Remdesivir was a result of very comprehensive NIH studies in partnership with the company, not for treating the SARS-CoV-2, but for treating the MERS, which is a Middle Eastern respiratory syndrome. While we're very successful, a very naive way of data science is to actually use the protein target and try to come up with docking result and claim success. Right, so in the early years, in February this year, I've seen a report that by a company using AI, try to dock these other drugs. Some of the drugs were earlier flares and lopinavir that turned out to be not effective during clinical trials. So people really understand that in order to do AI really well and make data science very relevant, you really need to understand the deep biology behind it. And it turned out, of course, this approach, simply relying on the RNA polymerase, is only, even in the case of remdesivir, is only effective in the case of early infection. And I was able to predict that even in February. And then what the clinical trial seems to be just simply confirming that. However, an interesting study published in February was using something different. And so this was published by Benevolent AI. I'm not affiliated with them, but it's a very interesting letter in Lancet that talk about collecting the knowledge graph by sifting through all the literature and understanding what a similar virus would do in the family. And then that would actually probably do something on the AAK1 and GAK proteins. So they found this rheumatoid arthritis drug that's called baricitinib that was approved by Lilly. And I think that then later on you see clinical trials that shows that this is very promising in treating later stages, especially when there's a cytokine storm related symptoms going on. So I think my point is, if you want to actually understand how to diagnose the disease and how to introduce drug therapeutics, you cannot take a very naive view of what's going on. You have to understand biology and deeper biology as you do the data science. So this figure was published recently in Lancet to show that the hypothesis what's going on in the whole process, from virus entry to infection, inflammation, and even sepsis, that's organ damage. On the left side is if the virus is mild, and even when the virus enters the cells, it can be easily cleared out by the immune system. It's a population of cells that include the T cells and other kind of antigen presenting cells, macrophages, and so on. And then the person will probably stop at asymptomatic infection stage, or at least at most it's a mild infection. But somehow for many factors, and some of our speakers also mentioned, the HLA subtype, aging, complication from other diseases such as diabetes and cardiovascular diseases. The immune system were not effective in clearing out the viruses. And so the viruses just exploded and trigger more and more cascading loop of so what's called a cytokine storm. And also due to the senescence of the immune system sometimes are too weak, sometimes are too overreactive. That's causing all kinds of damages in the heart, vascular system, kidney, and the liver. And that's why you see this disease become so severe. Even people survive, and then there's all kinds of complications and side effects to manage, some even for a lifetime. So how do we actually design data science strategies to treat that becomes a problem that puzzles the biologists and also informaticians? Let's take this, the human protein atlas as an example. At the early phases, we know that ACE2 is a receptor that assists the virus injection into the cells. But when you look at this database, the lung actually have a very low expression of this ACE2, whereas the gut has a lot, kidney has a lot, and male tissue have a lot. That created a lot of just confusions. And it was not until someone did the single cell analysis of the lung from the normal tissue, not even actually the COVID-19 patient tissue yet, because it was early. And then they found out that only the AT2 cells of the lung cavule, which is only a portion of the cells that have this expression of the ACE2. And all of the other cell type don't have it. So that really shows the challenge, and you really have to present the database accurately. You have to present the database in a specialized domain. You cannot simply just expect machine learning to be ready and plug in from day one when you have a new disease. This is a major lesson learned for this COVID-19. And of course, we want to do COVID-19 precision medicine. I think that one of the questions that we as informaticians think that you really need to address all of these questions. What type of cells may be affected? What are the major proteins that are responsible for viral entry and infection? How are our immune system affected? And then how are our immune system overwhelmed due to confounding factors such as aging and overreaction? And when and where does organ damage take place? And how can we develop a drug repositioning strategy at every stage of this disease, not just at the earliest stage or the too late stage and saving people, to achieve precision medicine? I think that's still a problem that many biologists are contributing, but can informatics contribute? I think we just take a very humble approach. We say, okay, I think whatever you do, you have to collect the omics data, functional genomic data. So if you actually can interpret the functional genomic data, or if we can help you interpret the functional genomic data better with a specialized knowledge base that contains things from the literature, wouldn't it be nicer? Right. In fact, this is what we did. And there's a web interface. We take up to 33 different data sources to build 11,000 what we call the PAGs. So essentially, these are super gene sets. And then we also build the relationship among these PAGs, and I'm going to talk about them in detail so that you can navigate from one pathway to another, especially when it's related to your query. Let me actually just go to the database and show you how this database works. It's very simple. For example, you go to here, you say, well, I'm interested in ACE2 protein. And then you do a search. It says the number of PAGs that's retrieved with ACE2 in the name is 3. But if it's a member, then there are 49. Let's just click on this. So on the left side, it gives you some query tools to say what kind of the super gene sets are available. And then you can actually say, I'm only interested in the one coming from PubChem. The PubChem contains a lot of a repositioning candidate of all the coronavirus drugs. Whenever people are claiming in the literature or having clinical trials, PubChem does compel them. So there are lots of pathways related to these. As you can see, this is a structure that I'm gonna click into this. And I see, well, this is a pathway documented by PubChem. And the PubChem actually annotated wiki pathway. Someone annotated coronavirus a wiki pathway. You can actually click on that. And these are the members. And then these are the gene-gene interactions within this PAG. And then there are also gene-gene regulation relationship. We do calculate some scores to give you a sense of which one of them is more significant. In this specific PAG, you can read up the documentations how we calculate the score, but essentially it's a centrality score based on network. So this gene is more important. One of the features that in our database that we feature is this related PAGs. So for every PAG, and then we also give you some recommendation, right? This recommendation is a relatedness. We can relate it by neighbors or upstream and downstream, and I'm going to come back to the presentation to show you more about it. Okay, so just a little bit about a PAG representation. Why do we use this as a representation? Many people in the bioinformatics will probably felt that when you're doing the DEG list, getting a gene list, and then all of a sudden, instead of converging on the standard set of analysis, you can go all over the places. You can check the pathway diagram to get the structure, or you can check your list against a prior annotated gene list that may have genetic aspect or proteomics aspect, has nothing to do with the RNA-seq, or may actually have a gene signature that's upregulated in some conditions. You want to check that, and then there's no standard databases. So many years ago, we came out with this concept and used a standard naming convention and notation to unify that. So in the PAGER-COV database, there are three categories of resources that we try to integrate. One is a repositioning drug and a target, mostly coming from a PubChem database. Right? There are 1549 targets related to PAGs. And then we also actually think that since the SARS-CoV-2 and COVID are new, so we've got to go to the literature to curate what the literature report are reporting about the genes and the pathways. And then we manually curated these and built it into the database. And we also think that it would be important to go to the standard database and then do a better querying. Instead of using COVID or SARS-CoV-2, which is actually not indexed yet, we can actually look for immune response, the cell types, the keywords, and systematically bring in only relevant content into this new database. And to make sure that our database is not contain just junk, we also introduced a previously published concept called the nCoCo score to measure the quality. Suppose that this is a database of all of the genes in the database, and within this dotted oval is a PAG. And then we calculate the number of interactions within this PAG against the background to see if there's enrichment. We also calculate the number of triangle of interaction relationship against the background. And then we add up the significance score together, and we normalize the score against the size of the PAG to make sure that there's no size inequality. And that's what the normal nCoCo score is. We actually calculated, if you actually draw this line to say this is a line that we previously determined to the right of which would be good, significant, highly relevant content. And as you can see, when you look at the P type, which is a pathway type we collected, they're all very high quality content. A type is annotated gene list. Mostly the papers contain them. They're very high quality. And the gene signatures that we sometimes bring in from other sources fall below, but most of them are still also very good. So that is a trustworthy database. And also we have this relationship between PAG and PAG are built by either neighborhood-based or M-type. Essentially, we're saying if we have two PAG, A and B, what are the numbers that they shared in common? If they shared in common more above the background, then we will actually put an edge between them. Okay, and then R type is if we know that there's a regulatory relationship between members of the PAG A to members of the PAG B, beyond that of in the background, and then we'll actually also put a significance between A and B. So those are all published method, and then we're simply borrowing them for this study. And then we also wanted to ask the question, should you even perform the GSEA against this new database, which seems to be smaller and only contain a few hundred more, or maybe I should just add this to a new existing database and call it done. Well, we did this comparison. We performed a GSEA test against the result, EEG result from a standard GEO database data set that's coronavirus related. We used the GSEA against a standard database called a PAGER that contains everything that the MSigDB has and also a little bit more. And also we compare it against the PAGER-COV. As you can see that they do have a significant overlap, which is the C, that are both significant. And then in the one that's only found in PAGER only, there are actually some of them are PAGER significant, but some of them are found, actually in this case, they're 0, so it doesn't matter. But in the case of B, for the one that's PAGER-COV significant, some of them are actually found in PAGER database, but they turn out when you are putting into the new smaller database context, they become insignificant in the result. And some of them are actually not found in the PAGER database. So my point here is just by looking at this result, a lot of the things that are uniquely found in the PAGER database turned out to be very generic gene signatures that's related to cancer immunity. And then you may doubt that maybe if you do pan disease studies, that will be of interest, but this is not for coronavirus related studies. For coronavirus studies, we not only were able to retrieve 43 freshly curated data sets out of less than 300, but also we see that these that were determined to be actually significant here in the PAGER-COV that wasn't actually determined to be significant due to the different database size difference and the way that we calculate the false discovery rate. So I think that I may run out of time, but I would really encourage you to go to this database and maybe even play with the advanced analysis function. In the just advanced analysis function, we allows you to enter multiple genes, perhaps coming from your own DEG list. And then you can find the similarity of your genes to some of the known ones. And perhaps you can pick some and do studies to investigate what is potentially up and down regulating of the gene set. And there's so many interesting findings that we're still finding, and hopefully this become your valuable resource for bioinformatics. Thank you.
Question? What's the backend database of this?
Yeah, we use Oracle 19c relational database for now.
Okay. And the main language is in what? The front end?
Yeah, the front end we use PHP.
PHP, okay.
Yeah.
How is the interfacing done? Like
How was the interface done?
yeah, like the computational pipeline are done.
Oh, the computational pipeline, we use a combination of Python code, R code, and Oracle PL/SQL to either pre-process them, store them into the database, or in some cases, and which we didn't show, we could do actually the analysis is done directly using our high performance computers and Python code in the end.
Okay, maybe we should move on to the next talk if no more questions. The next talk is the submission number 10. I will start to play the pre-recorded video. Let me see.
Hi, my name is Zhang. I'm a PhD student in Science University. In this video, I will present our work in biomedical knowledge graph of COVID-19, construction and applications. This is a joint collaboration between RD Healthcare in London and Science University. This talk will be split into 3 sections. I will first start by going over some preliminaries and introduce the background of biomedical knowledge graph and the COVID-19 dataset. I will then present our method for the construction of COVID-19 specific knowledge graph. And finally, I will introduce the modeling of the graph and its usage for job purposing and go over some experimental results. So let's first review the background of biomedical knowledge graph. Knowledge graphs are multi-relational data structures used to store facts about the world, which are widely used in industry that deals with large scale of data as they can serve as structured repositories of information. In this biomedical graph, node represents entities such as gene, disease, or drug compounds, and age represents relation between them. An example of such triplet in this knowledge graph is the tau protein is the target of Alzheimer's disease. Whether the head entity is tau, relation is target of, and the tail entity is AD. Using some computational models like knowledge graph embedding algorithms, you can infer novel associations with a tail entity relation query. For instance, what kind of drugs can prevent Alzheimer's disease? And the goal is to return the most likely head entity, such as the NAPA cell. Because of the benefit for the understanding of interconnections behind the biological systems, biomedical graph have played a more and more important role in healthcare practice and research. In recent years, they have been widely used in various applications, including drug purposing, target identification, side effects prediction, and so on. Although many efforts have been devoted to constructing journal biomedical knowledge graphs, most of existing works are populated via some form of manual curation, which is difficult to scale in the context of an increasing publication rate. As COVID-19 continues to spread rapidly across the world, it's urgent to find effective therapies to treat the pandemic. In response to the COVID-19 pandemic, the White House and a group of leading research institutes have prepared the COVID-19 open research dataset called 19 nCoCo. COVID-19 contains over 15,000 research papers with full text about COVID-19, SARS, and related coronavirus. Although a large amount of data is made available, it remains challenging for researchers to go through each paper and identify critical information from vast bodies of unstructured literatures. Automatic knowledge graph construction is an effective way to rapidly convert the complicated information of COVID-19 into a structured graph format, which can then be utilized to downstream applications such as drug purposing and mechanism analysis. However, there are no existing pipelines for rapid construction of a disease-specific knowledge graph. To this end, we established a pipeline for the semi-automatic knowledge graph construction performed with minimum supervision. We also conduct experiments on the constructed COVID-19 knowledge graph with various SOTA embedded models. And we discuss our observations across drug repurposing tasks and provide some insight and guidelines for how to use knowledge graph in the fight against this infectious disease. Having introduced the problem setup, I will now describe our approach for knowledge graph construction. The knowledge graph construction can also be described as a relation extraction. It's the process of detecting semantic relationships from a collection of raw text. There has been a lot of progress in unsupervised and supervised relation extractions recently, but they either suffer from the limited precisions or the requirement of well-annotated datasets. In this work, we leverage both of them by reusing the labeled sentence generated via unsupervised approach from PubMed publications and training a transformer neural network to identify the relationships of the sentence retrieved from COVID-19 with supervision. Particularly, the unsupervised approach is based on purchase work, global network of biomedical relationships, also named as GMBR. GMBR is a large but noisy knowledge graph comprising drug, disease, and gene entities linked by a small set of semantic themes derived from the abstracts of biomedical literature. Each TripNet has an original reference sentence and a support score representing the confidence of the relationships between those entities. Concurrently, we first filter the GMBR by identifying the largest collected component of the graph after removing any sentence that normalizable score is lower than 0.6. We further clean the GMBR by merging the trivial relation in closed clustering tree and discarding rare loads. Resulting training corpus comprise about 600,000 stripnets with detailed sentence description. Later, we used a transformer-based multi-classification model to train the knowledge corpus, where the input is a sentence with two biomedical entities and the output is the relationship theme between them. With a well-trained model, we can then predict the relationship of each pair of entity appearing in a same sentence retrieved from COVID-19. Note that we removed the sentence that did not contain the biomedical entities that have been existed in GMBR, and we only made a prediction for the sentences that contain more than two biomedical entities simultaneously. We combine all the TripNets from filtered GMBR and the based on previous work to achieve better performance in this after removing any sentence that normalizable score is lower than 0.6. We further clean the GMBR by merging the trivial relation in closed clustering tree and discarding rare loads. The resulting training corpus comprised about 600,000 stripnets with detailed sentence description. Later, we used a transformer-based multi-classification model to train the knowledge corpus, where the input is a sentence with two biomedical entities and the output is the relationship theme between them. With a well-trained model, we can the relationship of each pair of entity appearing in a same sentence retrieved from COVID-19. Note that we removed the sentence that did not contain the biomedical entities that have been existed in GMBR, and we only made a prediction for the sentences that contain more than 2 biomedical entities simultaneously. We combine all the tripnates from filtered GMBR and the COVID-19 to make up the COVID-19 knowledge graph. Top 10 or high quality knowledge graph, we only focus on the drug chemicals and the disease in DO database and the COVID-19 corpus. As for genes, we only keep those expressive genes that are often studied by researchers from BioGPS and collectivity map. Therefore, the COVID-19 knowledge graph consists of 15,000 entities of gene drug disease and 514,000 relationships of 27 types of relationships. Above is the details of the dataset. Here is the visualization of subsample of the COVID-19 knowledge graph and subsample of the chemical COVID-19 triplet. We can find the most related drug gene disease and the interaction mechanism behind them. In a high-quality knowledge graph, we need to apply it into downstream application. Knowledge graph embedding methods can thus be introduced to no-dimensional representations of entities and relations. The non-embeddings are then processed using model-dependent scoring functions to generate scores for all the triplets. Mainstream knowledge graph embedding approaches can be broken down into 3 different categories: transitional distance-based, semantic matching-based, and neural network-based. Here, we also developed a neural attentive graph embedding model, HRGAT, based on previous work to achieve better performance in this dataset, and use it for the drug repurposing hypothesis generation. For the time limit, we will not describe our embedding method here, but we will report the current NIC prediction results of the mean recipient rank and hit ratio at 1, 3, and 10. We think that our model can outperform other embedding methods in COVID-19 knowledge graph. To assess the capacity in drug repurposing, we also calculated the AUC and AUPS curves for the task-related relationships like inhibits and treatment based on the predictive score. As shown in the figure, our model performs well in discriminating the positive and negative triplet pairs of drug repurposing task. The 10 highest scoring drug repurposing candidates for COVID-19 are listed in the table. It's shown that most of the top-ranked triplets has been validated as effective to COVID-19 by external literatures. By presenting the 10 shortest paths between head entities and tail entities, we can learn more about the mechanism behind the predictions. It's worth to note that, according to the recent BBC News, dexamethasone can help save the lives of patients seriously ill with coronavirus. To summarize this talk, we constructed a COVID-19 biomedical knowledge graph performed with minimum supervision on a flexible pipeline. It can also be used in any other disease-specific knowledge graph construction. We also conducted experiments on the proposed COVID-19 with various SOTA embedding models, and we discussed our observation across drug repurposing tasks and provide some guidelines for how to use knowledge graph in fight against this pandemic. I'd like to end the presentation by saying that part of our source code is online, and please feel free to reach out to me if you have any questions. Thank you.
Question? The presented Mr. or should I Shuang are you joining from China? Just curious.
So Shuangjia won't join this meeting. So I'm Xianglu Xiao, and I'm here for answering any question regarding this.
Okay. What's the best way to share the graph data set? If you generate the graph data set you want to share, what's the best way now we can share the graph data set?
What do you mean by share?
Well, I mean, we have code we can put on GitHub. We have sequence, we have sequence deposit. How about the graph data set?
I think we are currently creating a backend and a front end for directly to search on the graphical data set. So on the knowledge graph, and we also create some link prediction tools, which researcher can directly use the data set.
Mm-hmm. Okay, if no more question, we move on to the next submission, that's number 13.
Hello, everyone. This is Curation from Q University, Germany. I'm representing our 1.3 acres COVID-19 to present our paper, COVIDNet, to bring data transparency in the era of COVID-19. Today, I'm going to tell the story on how a group of data scientists and engineers have helped to bring data transparency in the COVID-19 pandemic. Before I started, I would like to dedicate special thanks to 1.3acres.com for initiating and hosting this project since the beginning. So you may wonder, what's the COVIDNet? We are an integrated information platform focusing mostly on the COVID-19 pandemic tracking. At the core of our project is, of course, a real-time COVID-19 case dataset. Here is a screenshot of our website landing page, assuming you are accessing it from within the United States. We will dive into these components later in the talk. Before we move on, one may think this is simply yet another visualization website, and why bother discussing it here today? To answer your question, let's take a moment and go back to the late January, when the COVID-19 has just started to soar across the world and in North America. Back then, the communities were worried and somehow in panic with the outbreak of COVID-19. And individuals desperately needed incredible and local information. At that time, there were, however, no aggregation platforms providing such a full picture of the situation in North America, in both official channels and unofficial channels. I would like to emphasize that by far, we're one of the major independent COVID information aggregation sources in the world, and especially in North America. Our dataset has empowered most mainstream trackers like Wikipedia, Johns Hopkins North America platforms, etc. Here is a showcase of platforms and institutions we have provided data accessing support. So what we're trying to address with our project is to tackle three major challenges that data could help in the pandemic like COVID-19. Specifically, public wants fresh data that can represent the latest situation. This is critical for each of us to take responsive actions. Individuals and local communities really want to understand the situation around them to make local policy decisions. In another word, we need finer geographical granularity so people in each county, each city can make use of such information. Last but not least, rumor from uncredible sources would generate panic, or on the contrary, didn't raise sufficient attention. So we should aggregate and provide credible sources and always perform quality control over the rapid growing situation. By far, with our full voluntary team, we have achieved solving these challenges in about 50 countries across the world. Our website alone has been visited more than 240 million times by May. Our data API has been used by more than 600 research institutes. Oh, before I forget, our API is free of use for research purposes. We welcome everyone to use the dataset to help fight the COVID-19 pandemic. Next, I'd like to show some key milestones in our projects. On February 5th, we launched the initial version of the COVIDNet project right after the first reported case in North America, and hits 1 million users by February 28th. Since May, we have spent many of our resources on extending our platform to a fully global tracker. Here is a summary of the key statistics of our data as of July. We collected from 1,064 county and city level sources in North America and 52 governmental data sources in 49 countries and territories. I want to point out that this is the current situation after we have built an automated pipeline to fetch data and manually apply quality control. However, this was not feasible at the beginning since the local health authorities have not yet established relatively stable data sharing schemas for the first 1 or 2 months. During that time, we have spent lots of work trying to bring the data transparency gap, and our data collection have underwent a few different stages. At the beginning, with the initial outbreak, our group of volunteers have actively searched all media and official channels for case updates when the new cases were sparse. Later, when the case has started to accelerate and rapidly grow, we have incorporated crowdsourcing channels. Our users started to report new cases and local news on our websites. Our team will immediately follow up with the information and check the credibility of the information before updating our website. During this period of time, we have received over 16K information leads. Note that such crowdsourcing is combined at the same time with our semi-automated data pipeline, which we have gradually developed. Starting April, we have mostly transformed to automated data collection. However, I should emphasize that our volunteers do manually check the validity and correctness of the data due to the potential noises in the raw data source before updating our front end. I shall briefly discuss some key features when our platform evolved into a global COVID tracking project starting late April, where we have extended our toolset to collect data in over 49 countries and territories and supported multiple languages interfaces on our website since then. The data quality control is always the first priority of the COVIDNet project. Why? Because there is always potential noise and numerous data added, even in official data sources, especially prominent in North America. To ensure the data as accurate as much as possible, we have adopted 3 layers of data quality control. First, the volunteer individual checks the data source. On top of this, other volunteers check the information as peer review. Finally, before updating the web page, we have a set of rules to avoid abnormal changes in data. There are more details I would like to share. If you are interested in, please refer to our paper. Our project also offers a wide range of visualization tools to illustrate both temporal and geographical trends of the COVID cases. Most of them are interactive. I will encourage readers to explore more on our webpage. Here are some examples. The left side of the graph showed active and cumulative case in time series. We can easily find the patterns of the outbreak and spread situation in these two countries. The right side is a geographical map showing the levels of severity in each state. Users can also zoom in each state and see county level maps. Here is another graph where you can compare the trends and patterns across different countries and regions. Before concluding this presentation, our team would like to thank a number of teams that have helped us along the project. Last but not least, the COVIDNet project is in the hard work of a great team of volunteers. It is a privilege to have worked with such a great team. Thank you so much.
Question? Any presenters here to answer questions?
Hi, this is Kaishan, and I'm representing our team to answer the questions. So,
oh, great, thank you. Where are you joining from?
Joining from?
Yeah, where are you from?
Yeah, I'm right now in Seattle.
Oh, I see. Okay.
No.
I heard. I actually have a question or comment. In your presentation, you mentioned data are problematic, and you also comment especially from North America.
Yes, I would say that our tracker first started and focusing on North America. So as a beginning, when the pipeline and the tracker was forming, it is exactly the time we built on our experiences on. So that's why we have like experiences all kinds of like challenges and in that part. So later, when it comes to World Tracker, we are pretty mature, and so yeah, that's why it is much easier in the when time passed. And since the spread of COVID-19 is a fast evolving situation, it is almost impossible to like pre-design a perfect system to collect and present case information. So this is the same for the local authorities. So yeah, that's we are growing and expanding as the pandemic grows. So yeah. So this is the same for the local authorities as well as us. So yeah, we are collecting the information from them. Yeah, that would be my answer.
Okay, so, any other questions? Okay, if not, we will. Well, actually, we are ahead of time. Are you still rely on the heavily rely on manual curation now?
We are right now processing the combination of automative and manually support, because automative can largely increase the efficiency. Meanwhile, for the quality control reason, we have to make sure every data updated are the most secured. Therefore, we have to like have our volunteers to come up and double check if the data is correct before updating the website. yeah, so it is the manually work is essential to like make sure the data is accurate.
Yeah, so this is Diane. I have a question. So according to what you just mentioned, so these numbers are actually underestimated, right? So there's still like more cases actually happening. To confirm the cases are more like the safe cases. Am I correct?
Sorry, if I understand it correctly, we always focus on the local data, like our data source are local health authorities, wherever they are in North America, in worldwide levels, we collect data from authorities, local health authorities. Yeah, that's it.
So you mean that local authorities, some data may still need manual checking because there are still mistakes?
Yes, that's right. Because, for example, in May, we experienced some local data changes from Spain. They changed the criteria for the cases, like for they changed the criteria to tell if this is a patient or not. So the number changed a lot, like changed 1/3 of the numbers. So all of a sudden the number crashed, like from a high level to down. So therefore you have to double check on a web page, like you have to have like automated system to tell, well, there is a big change in the data from yesterday to today. So a volunteer have to double check. Then we found out there are some changes from the authorities from the region. So yeah, that's the story happened in May. Yeah.
I see. Because it's a change of criteria, right? So do you use all the same criteria for all the local authorities, or do you follow their change of criteria, or you actually preserve the previous criteria? How do you handle this case?
Yeah, actually, we are a very big voluntary team, and we have one specialist who's really focusing on this area. To answer the question, we did a lot of researches on the criteria for different countries and different regions. So we are basically following the same standardization by ourselves. Yeah.
Thank you.
Yeah, thank you so much for your interest and the question. Thank you.
Yeah, it's a very impressive system.
Thank you.
Okay, if no more questions, let's move on to the next presentation. The next presentation is towards a clinical knowledge-based question answering data set. That's paper number 23.
This presentation is a brief overview of the project Creating a Clinical Knowledge-Based Question Answering Dataset, which is a collaboration between MIT and IBM. The problem that we are trying to address at a glance is that the longitudinal domain-specific nature of electronic medical record data, along with the privacy concerns, makes it difficult to develop large-scale annotated datasets. In order to address this, we generate EMR-KBQA, which is a knowledge-based dataset for question answering on patient-specific structured electronic medical record data. The EMR-KBQA work builds upon the EMR-QA work. For context, the EMR-QA dataset was developed using a semi-automated process to answer physician questions on electronic medical records. EMR-QA is the first community-shared large-scale dataset for patient-specific QA that was built leveraging I2V2, a dataset of expert annotated clinical notes used for several NLP tasks. In this work, we generate EMR-KBQA, a dataset for QA on patient-specific structured EMR data, which expands on this EMR-QA dataset to knowledge-based question answering by leveraging structured data in the MIMIC3 database. This is a brief overview of the MIMIC3 database. The MIMIC3 database contains 49,875 hospital admissions, of approximately 38,597 patients who stayed in the ICU at Beth Israel between 2001 and 2012. It includes information such as demographics, vitals, lab test results, procedures, medications, caregiver notes, imaging reports, and mortality information. It also includes high temporal data and electronic documentation, as well as bedside monitor trends and waveforms. The process for generating the EMR-KBQA corpus comprised of 3 parts. The first one was collection of question and logical form templates. To generate EMR-KBQA, we leveraged the question and logical form templates from EMR-QA, which were created from questions posed by physicians and subsequently normalized. The second step was template curation and mapping entities to MIMIC3 structured data. To do this, we filtered out the templates that could not be answered from MIMIC3 structured data. In general, MIMIC3 structured data does not capture relational information across tables. The entities in the remaining question and logical form templates were mapped to the MIMIC3 columns. The third step was template filling and answer extraction. We populated the question and logical form templates with values from the MIMIC3 tables. This is a summary of the generated EMR-KBQA dataset. It comprised of approximately 440,000 question-answer pairs from 359 question templates and 31 logical form templates using a sample of 100 patients. This data set is in progress and continues to expand. Of the generated data set, 87% were test results, 12% were medication-related results, and 1% were condition-related results. On average, 14 question templates mapped to a single logical form template. This is an analysis of the EMR-KBQA dataset. Of the 92 logical forms available from EMR-QA, 31 could be populated with MIMIC3 structured data. These included questions around lab events, procedure events, chart events, medications, and conditions. 50 could not be populated from MIMIC3 structured data. This is due to the missing relations or the type of data being unavailable. These include questions around symptoms, family history events, or node events. And finally, 11 of the templates could not be populated in MIMIC even when the type of data exists, and this is due to missing fields. These include questions around diagnosis date, pending diagnostics, adherence, SIG, and dosage, all of which are unavailable in MIMIC3. We implemented the system with around 50 SQL scripts and several shell scripts for the end-to-end process. The data was stored in Postgres, and certain tables within MIMIC are very large, such as the chart events, and these were partitioned for better performance. There were several challenges that we faced. One of them was handling temporal questions, and we had made several assumptions in order to be able to answer these questions for every patient. In addition, we had to curate relevant types of labs, treatments, and vitals so that they could be answered from MIMIC data. We avoided making the responses MIMIC specific, as we hope for the system to be deployed to other data sets as well. And finally, there are certain questions that could not be answered, such as those around allergies and smoking histories. A subset of them can be answered, but not all of them could be. In the future, we hope to address three things. One of them is to generate a data set that combines structured and unstructured data so that it is more representative of the complete EMR of a patient. Second is to expand the data set to include more commonly asked physician questions. And finally, we hope to train a semantic parsing model for question answering on EMR-KBQA dataset. Thank you.
Is the presenter here to answer questions?
Yes, I'm here. Can you hear me?
Yes, great. Questions? Is there a general API for people to use, or this seems to be a Postgres database? Or?
Yeah, so we would be having APIs eventually, not at the moment.
Mm-hmm. How large is the Postgres database if you want to dump it?
How large is it, or how?
Yeah, the file size, like.
It was, I think, around, like, just the chart events was around like 50 gigs.
50, okay. Other questions? It looks like someone wants to join. What's the future direction of this database?
So the big thing is right now it's very focused on structured data because we're using Mimic, but it would be nice to expand it to more unstructured data. So for that, there's like certain data sets available with physician notes, and combining the like note related data with this would be more representative of like all kinds of questions. So the next step is using is kind of combining the unstructured components as well. And also, sorry.
My question is, why did you select Postgres database? Is there an advantage?
Yeah, that's a good question. I think the big reason was there was great support. Like if you look at the Mimic documentation and the Mimic scripts that are available, Postgres is one of the easiest one for like really easily getting it running at like right away.
And what type of operation you are going to do on unstructured database?
What operations? Can you
queries, like what type of queries you are going to do in the database?
We did a lot of joins across like the various kinds of tables, like the chart events with the patients and chart events with like the dictionaries and all of that. So like, yeah, mostly joins with like multiple tables.
I have a technical question. For the database, does it contain the patient demographic, like white, Asian, those kind of information?
No, the Mimic database, from what I remember, it contains like age, like even age, like it's kind of de-identified, but like I don't think they have demographic information.
Okay, if not, let's thanks the presenter. Let's move on to the number 27. That's the menu. So the next presentation is the number 27. That's curation at a scale computational approach to support curation in lit COVID. Okay. It looks like someone have their microphone on. I have to mute everyone. Oh, it's muted. Okay. Sorry.
Hello, everyone. I'm Qingyu Chen from National Library of Medicine, National Institutes of Health. I'm a postdoc fellow from Dr. Jun Lu's lab. My research interests include biomedical text mining, medical image analytics, and biocuration. Today, it's my great pleasure to introduce LitCovid, a web server dedicated to COVID-19 literature. Specifically, I will introduce the functions and features supported by LitCovid. I will also introduce the curation pipeline of LitCovid. We have been using a combination of manual and automatic curation to support daily updates in LitCovid. I'm also very happy to introduce my colleague, Dr. Alex Allott, who will also join us at the live QA session. COVID-19 has been impacting everyone. So far, it has caused over 12 million infection cases. It has caused over 500,000 deaths. It is urgent that we can get latest information from literature. For example, what is the latest finding of diagnosis? What kind of symptoms could be considered as COVID-19 positive? What are the case reports representing specific or individual patients that has been diagnosed as positive? What are the latest updates on treatment procedure? And any latest findings or results on vaccine demand? Also, what kind of the general recommendations on prevention and control? All those information were documented in the latest literature that we need to have a fast and efficient access to it. So we need a specialized resource just on COVID-19 literature. For example, there are many massive amount of COVID-19 related papers. We need to support a quick exploration or navigation to them. We need to make sure the resource have a well coverage on COVID-19 papers. We need to have dedicated features, for example, for topics, for visualizations such as world maps or important entities such as chemicals. I want to briefly show you. For example, this is before the name of COVID-19. So those are the terms mentioned in the literature to describe COVID-19. There are more. So this is after COVID-19. And there are even much more. So you can see for a same disease, same coronavirus, there's so many different ways to introduce. There's also, in another way, it demonstrates the importance of a dedicated literature resource that provides a well coverage of COVID-19 related papers. So here we introduce LitCovid. It's a curated literature hub for tracking up-to-date scientific information about 2019 novel coronavirus. It categorizes the latest literature by topics, for example, like mechanism, transmissions, treatments. It also supports visualizations or quick navigations, for example, supports weekly overview, for example, to see how many papers are indexed each week. It also shows the number of papers by country. This is the home dashboard. For example, you can search free text via the search box. You can also, for example, navigate to topics. You can see you can click and access the weekly publications. You can see the latest publications, and also there's a world map, as I mentioned. It supports search functions for LitCovid. So you can have all search, you can have end search, not search. It also supports phrase and phrase searches. It uses synonyms. It customized stop words specific for PubMed literature. This is a .sum page. It shows a list of literature, and you can do the two types of sortings. You can sort by relevance. If you type a query, it sorts by the time of creation date. It has different filters. For example, you can filter by the chemicals mentioned in the paper. You can search by the journals. You can search by the countries. So it also supports visualizations on the publications and countries. You can also download the papers. You can also subscribe to the interested papers. For example, the query that you're interested, you can subscribe. You can get daily updates for that. This is the abstract page. For example, when you click a specific paper in the .sum page, it will lead you to the abstract page. It will show the abstract if it's available. It will show full text link, user-defined keywords. It will show or visualize the mentioned countries. It will show the similar publications. You can also tweet them into Twitter or Facebook. So we use more like this function to compute the similarity. So remember, we just showed you the similar functions, similar publications in the abstract page. It uses title, abstract, author provide keywords, and also topics to compute the similarity. So it supports like 3 types of downloading functions. First, you might just download them to a RIS file so that you can directly import to reference management software. It supports TSB format that you can directly use them for automated software. It supports text mining, so it has automatic annotations used by PubData. So for example, it will show you that, for example, mention genes, mutations, those things mentioned in the literature. So this is the ISS feed as I mentioned, so you can subscribe to with your favorite ISS reader. So you can do it for all applications, or you can do it for a specific query that you're interested. So now I'm introducing the daily update pipeline. So every day we retrieve the latest publication by PubMed EUT. Okay, and then we do a document classification to classify the related papers that are related to COVID-19. Only the papers that are related to COVID-19, it will go to the next stage. Then we will annotate topics. For example, is it related to diagnosis? Is it treatment? So on and so forth. And then after we do, during this step, then it's a combination of automatic tools and also manual curation. And then we will do geolocation tagging and also chemical extractions. After that, we index in Solr. That means basically it will be in the production system. It will show the latest paper for that day. So this is the pipeline, okay? We retrieve the publications every day. We classify them, whether they're related to COVID-19. We curate them, both automatically and manually. Then we export them to the production system. So the first one is classifying publications. It's a 2-step process. First, we use a broad query to retrieve publications as much relevant as possible. Okay, so for example, we will have like the keyword coronavirus to retrieve any publication on coronavirus, not only COVID-19, because we want to give a broad coverage at the first step. Then, second step, we use machine learning and deep learning models to classify whether they are related to COVID-19. In other words, the first step, we generate a broad list of candidates. The second step, we do it in more depth. So we classify only the COVID-19 related papers for curation. So we developed convolutional neural network, random forest, and SVM for the document classification step. And we use an ensemble approach to get the average prediction score for each document. So we did the classification, we did the evaluation on document classification. This is a training test data set. The performance is pretty high, so precision is almost too perfect. Recall 0.98, F1 score is 0.98. After classifying the related documents on COVID-19, then we will assign the topics. As we mentioned, it's like there are 8 broad topics. For example, general information, treatment, forecasting, transmission, etc., etc. So for each topic, for each document, it will classify 1 to 8 related topics based on the text, okay? And then it gives the probability. So far we have used logistic regression to predict the 8 topics. Recently we developed a deep learning model, use BioBird and many crafted features, which further improves the performance. So this is a screenshot that we do for annotation. So you can see the topic classification models already give their predictions with probabilities of the topics, and it's for human review. So these are the evaluation performance. So precision is about 80%, recall is slightly over 80%, F1 score is 80% for the 8 topics. And also we are doing geolocation tagging, as I mentioned, is like we have the countries mentioned in the abstract. So this one, we directly use a pre-trained location tagging model from space. We directly apply it. We didn't do the fine tuning. So after we directly apply, we get the predictions, then we post-process them. For example, we group the location into countries. We try to remove some false positives, etc., etc. So we are doing some post-processing use some tools. So this is the performance. Because we directly apply it, so there's no training testing data set, we mainly annotate over 300 articles that with like countries mentioned. So again, this performance is also very high. So precision is 0.96, recall is 93, F1 score is 94. So in summary, we have introduced LitCovid. It's daily updated since February, dedicated on the latest publications on COVID-19. It has millions of hits per month. It's cross-referenced by hundreds of universities, research institutes, and libraries. Because we're doing updating daily, so we use a combination of automatic models to support menu curation. As I showed you, there are 3 main automatic curation parts: document classification, topic classification, geolocation tagging, and I showed you the evaluation performance for each one. There are still some challenges that really require menu curation efforts. For example, now the LitCovid has over 30,000 publications in total, and every week it has more than 2,000 papers. Topic classification, as I showed you, okay? So document classification and geolocation tagging, they have almost perfect evaluation results. But for topic classification, first, because we predict to 8 topics, it's a multi-label classification, it's quite challenging. Second one, there's some publications, I think it's about 40% publications, they do not have abstract available. So basically that means the models can't access those abstracts. We really need human curation. That means it's like we need to have annotators or curators that manually check the abstracts of the articles. So we look forward to feedback and interesting ideas to work with. So existing studies have used LitCovid in bioinformatics related applications, such as creating knowledge graphs or drug repurposing. And we want to present LitCovid to bioinformatics audience and look forward for further collaborations. So finally, we really appreciate our users. You have been motivating us to keep up the curation and keep up collecting the literatures every day since February. Thank you so much. Thank you for your attention and look forward to your comments and questions. Thank you.
Are the authors here to answer questions?
Yes, both me and editors are here.
Okay, thank you. I have really appreciate it. I have to also say that I also use the site. Really appreciate this.
Yeah,
Thank
so
you.
this is Jake. Really a very nice work. I started using your work since the day you published the letter in Nature, and I've been enjoying it. My question is more on the design, the future perspective side. I find this is a very interesting niche application of PubMed, but at the same time, not all the NCBI searches are as nicely done as this one. So I wonder if in the future, this is going to become a model for PubMed to do all future domain-specific searches, such as cancer, Alzheimer. Are you gonna actually create domain-specific interfaces just like this in the future? Or do you feel that this could actually become more generic search interface for NCBI database of tools that can actually, when you search a specific topic, you share this and you can search for essays in PubChem, and you can also search other genes or SNPs in other databases.
Yeah, thank you for your question. So first, we are not forecasting models, so we don't know, exactly it will be in the future. But I can tell you that we have been discussing the future of LeetCovid. It's like the general or big picture is like it might be served as a model for for emergency or disease portal. So that means if any pandemic happens, it can be react rapidly within weeks. That's the general picture.
Okay.
I have a technical question. I noticed you put the geolocation prediction there or analysis there.
Yeah.
I'm a bit confused because when people publish, they have an affiliation. Wouldn't that already give a location something?
Oh, thanks for that. Just for clarification, all the geolocation headings for the places mentioned in the abstract.
Oh, I see.
Yeah, thanks for that.
I had a question. You mentioned that there were 8 categories. Which of those 8 were like, most of the times the manual annotators had to end up tweaking more? Like, is there a certain category that was really difficult to get right by the automation?
Yes, that's a great question. So it's like if you see the papers, many papers are related with category like treatment and prevention. So there are very few papers, relatively speaking, is transmission. So though it's like if you use it's kind of the data imbalance. That's one thing. So if you train the model, it might be so if you have a lack of instance for training, that the prediction or the performance might be lower for that topics. The other thing, as I mentioned in the video, is like some of the papers they do not have abstract available. So so it can't be used for training at all. That needs human curators to manually check.
Thanks.
I noticed you put the convolutional neural network model in one of the pipeline. What's the input? What is the input layer for that convolutional neural network?
Input layer is the title plus abstract. So each word in the title and abstract, and with their word vectors. The word vector is the word embedding trained in PubMed.
Thank you. Any other questions? If not, it seems to be we can have a lunch break. Jack, what do you plan to do the lunch break?
Well, I think that we're gonna just do a social networking, something fun until the next session start. So I would just say, people, if you can, if you're in the home, grab a sandwich, grab your food, and turn on your video camera. I just have one slide as a starter to show, and then we can just